Howdy everyone, and welcome to lecture number 41, which is going to conclude our semester, this semester of internal combustion engines. Okay, so I'm recording this from the airport. That's why I'm using a somewhat lowered voice, but I'll be sure to speak loudly enough that you can hear me. And if you recall where we left off when we finished our last in-person class, lecture number 40, is we had just completed discussing the various factors that influence laminar flame speed. And if you remember, we said that laminar flame speed is the primary feature of a fuel-air mixture that affects the flame initiation period. If we know how laminar flame speed behaves, we'll be able to predict the corresponding effect on flame initiation period. But then we also recognized that if we rely solely on the laminar flame speed, something that's burning at, say, 40 centimeters per second, to burn the entire fuel-air mixture of a typical internal combustion engine, this laminar flame speed is way too slow for us to be able to burn the complete mixture in the allotted time that we have during the cycle. And so the question then becomes, well, how is it that we're able to completely burn a fuel-air mixture during the few milliseconds that we actually have during a combustion process in an internal combustion engine? And the answer is that the mixture very quickly becomes what we call turbulent. And turbulence is essentially what allows that flame that initiates during the flame kernel development period or the flame initiation period to rapidly proceed and engulf the whole fuel-air mixture and be able to burn that fuel-air mixture very quickly. And so essentially what happens is you have turbulence that allows the flame to very quickly spread throughout the mixture, and you create essentially small burning zones throughout the entire mixture, where those small burning zones then burn as governed by the laminar flame speed. So a good analogy that allows us to visualize this is the ink roller diagram that you see here in the bottom of your slide. You can basically see that you have a series of ink rollers. That's what each of these little circles represents. For just a moment, ignore that black dot that says the initial ignition site. And you can imagine that if this ink roller is rotating in this direction, that's going to cause this ink roller to rotate in this direction, and this ink roller to rotate in this direction. And then, of course, that action is going to cause this ink roller to rotate in this direction, and correspondingly this ink roller to rotate in this direction, and this one to rotate in this direction, so on and so forth throughout the whole matrix of the ink rollers. So if you imagine your fuel-air mixture being composed of a bunch of small eddies, right? So suppose this is your whole cylinder that you have, and within your cylinder you have small fuel-air eddies that are basically little pockets of fuel-air mixture that are just rotating within the mixture itself. You essentially have this idea of turbulence established throughout your mixture, okay? And so then, if you have a small ignition site, say you have a small flame right here where this black dot is, where you have some development of a flame, what happens is that the ink roller above this ignition site, which is rotating this way, or this fuel-air eddy, which is rotating in this direction, is going to carry that flame with it in this clockwise motion, right? And likewise, the eddy, the fuel-air eddy, that fluid motion below the ignition site, is going to carry the flame in this direction, right? And then, of course, as you can see, that as this eddy is carrying the flame upward, it then interfaces with this eddy here, and now this eddy is going to begin to carry the flame in this direction, right? And then, of course, it's going to interact with this eddy here, which is then going to carry the flame upward to this direction, and then finally it'll ignite and spread the flame to this last eddy, which is on the outer periphery, right? And you can carry that same thought experiment through each of these eddies, where we have transferring the flame to this eddy, and then to this eddy, and then to that eddy, and very quickly, by this rotating motion of the fuel-air mixture, this turbulence that's established within the fuel-air mixture, we can very quickly spread the flame throughout the entirety of the fuel-air mixture. And so you can kind of see that when we look over in this diagram in the center, right, where the flame initiates here in the center, and then it rotates and it transfers to this eddy, and it transfers to this eddy, which then allows it to transfer to this eddy, and then to this eddy, right? And you can basically see that these black squiggly lines is essentially that flame transmitting to the entirety of the fuel-air mixture, right? And so by the time that this one fuel-air pocket in the center of the mixture completes one full rotation, you can see how much the flame has spread throughout the mixture, right? And so that's the idea of turbulence, is that essentially we're very quickly able to spread the flame throughout the entirety of the mixture. And then once you have a fuel air eddy engulfed in flame, well, now that eddy can, being a much smaller diameter, it can burn laminarly, right? It can burn as governed by the laminar flame speed, but your distance is much, much shorter, right? Each of these eddies are on the order of, say, micrometers, right, if not smaller, compared to the usual dimensions of say, the stroke length and the bore diameter of a cylinder, which is measured on the order of millimeters, right, if not tens of millimeters. And so you're very quickly able to spread that flame through the whole mixture and be able to burn it up, burn it up in a much more rapid fashion, thanks to turbulence. Okay. Okay, so how do we model that? How do we model this initiation of the flame in the center portion of the mixture, and then rely on turbulence to transfer that flame throughout the whole mixture, and then be able to do this burn up? Well, this is where we come up with our rapid burning model, right? So if you remember, there were two portions or two phases of our combustion process that we described. The first is the flame development period, the flame initiation period. That's where we basically try to create this ignition site in the mixture where there is a flame that develops. And then there's the rapid burning period. And the rapid burning period would then be the spread of the flame throughout the whole mixture, and then the subsequent burn up of that mixture by burning up each of the individual eddies. So we model that 10 to 90% burn period, or we model this rapid burning period, or we call that rapid burning period the 10 to 90% burn period, right? So this is what we would generally call our combustion duration. And we model this by looking at two different elements. The first element is the is the entrainment rate. And the entrainment rate is this first term that you see here in our equation, this dme by dt, okay? And so the dme by dt, this is basically the mass of the mixture that is entrained by a flame as a unit of time, right? And so we can say that dme by dt is the mass entrained by flame as a function of time. So if we go back to our ink roller example, basically the mass entrainment rate, that dme by dt, would be the rate at which I pass this flame through all of my various eddies throughout the whole mixture. Okay, it's how quickly can I entrain each of these eddies with a flame. Okay, that's my dme by dt. The second portion of the rapid burning period is the actual burn-up rate, and that's the second equation that's shown here, the dmv by dt. And so dmv by dt is the rate at which entrained mass actually burns. Okay, so we'll come back to the burn-up rate here in just a moment. But to first diagnose the entrainment rate, okay? So in order to predict what's going to happen to the entrainment rate, just like before when we wanted to predict what was going to happen to the laminar flame speed, we looked at things like the effective fuel type and fuel air equivalence ratio, the unburned gas temperature, and the unburned gas pressure, right? The pressure effect. We also want to look at what the various factors that are affecting this entrainment rate are. And there's basically four factors that affect the rate of entrainment. The first is the density of the unburned mixture. The second is the flame front area, AF. The third is the turbulent intensity. And then the fourth is the laminar flame speed. Okay. Now, one quick thing to note is that even though within this parentheses, this term, we have the turbulent intensity plus the laminar flame rate, generally speaking, that turbulent intensity is much, much larger than the laminar flame speed. And so whatever we do to enhance the turbulence of the mixture is going to enhance the rate of entrainment, the entrainment rate of that mixture. Okay, but basically what you can see here is each of these terms has a direct influence on the entrainment rate. So if I increase the density of the unburned gas, say if I increase pressure or I decrease temperature, then my density increases, and that's going to increase my entrainment rate. If I increase my flame front area, suppose I move from a center-mounted spark plug, or excuse me, a side-mounted spark plug to a center-mounted spark plug, that's going to increase my flame front area, and that's going to increase my entrainment rate. Suppose I increase my turbulent intensity. I increase the amount of turbulence that I have in my mixture. I increase the number of those eddies that I have in my fuel-air mixture. That'll increase my entrainment rate. And then finally, of course, if I increase my laminar flame speed, that'll also correspondingly increase my entrainment rate. Okay, now we'll come back to each of these four terms and talk about how specifically these various factors influence the entrainment rate. But the other piece to the rapid burning period is the actual burn-up rate, this dmB by dt. And this is a simple differential equation that just looks at how much mass has been entrained minus the amount of mass that's been burned, divided by what is called the burn-up time, okay, this tau b. And this tau b is defined down here at the bottom of the slide as being lambda, which is the diameter of each of those individual eddies divided by the laminar flame speed. So if you can imagine, if we go back here to our ink roller example, right, if you imagine that each one of these little circles is a fuel-air eddy, and so we can go ahead and define, say for this fuel-air eddy, a diameter, and this diameter is basically lambda. And so essentially what happens if I just kind of expand this out a bit so that we can kind of more easily see what's going on. Suppose this is my eddy, and it's covered in flame, thanks to turbulence. My turbulent entrainment basically engulfed this little fuel-air eddy in flame, and it has a diameter lambda. And this flame is going to burn inward and basically consume this eddy from the outer diameter in at the rate of the laminar flame speed. Okay, so that flame is basically going to move and consume this entire eddy from the out to the in at the rate of the laminar flame speed, right? This is S sub L here, okay? And so that burn-up time, that tau b that we define here on slide 12, is that eddy diameter, this diameter here, divided by the laminar flame speed of the mixture, which of course we've already previously diagnosed when we were talking about the flame initiation period, okay? The other terms, mass of entrainment, that of course depends on the entrainment rate, right? So you don't have entrained mass until you have the entrainment rate obviously being positive, and then the burn-up mass, the burned mass, is going to depend on your burn-up rate, right? And so MB doesn't become non-zero until you have entrained mass, and then of course the burn-up rate, right? And so as you can imagine, initially this dmB by dt starts off small, increases rather drastically as the entrained mass increases, but the burned mass is low. But then as you entrain mass and you burn it at the burn-up rate, then the burned mass eventually starts to rise up and eventually begins to meet the entrained mass, and then the burn-up rate eventually decreases and then finally goes to zero as the burned mass equals the entrained mass. Okay, so that's the model that we'll use to diagnose, to predict what our mass fraction burn curves are. So let's go ahead and evaluate how each of these terms might be influenced by the design of the engine. Okay, so factors that affect unburned mixture density, right? These would be all the things that you would generally expect them to be. Your initial temperature of the cycle, for example, right? So a lower unburned mixture temperature, TU, will tend to increase your mixture density, okay? Your initial pressure, right? So a higher uh, uh, unburned pressure will tend to increase your unburned density. And one thing that we have to pay real close attention to is compression ratio, right? Because what happens is we change compression ratio, as we say we, for example, increase compression ratio, what ends up happening is you are increasing both your pressure as well as your temperature, right? And so we'd have to think very carefully, what happens when we increase compression ratio? Does that ultimately raise my mixture density, or does it lower my mixture density, right? And so generally speaking, as you raise your compression ratio, you're ultimately going to be raising your mixture density, because we assume that you're starting with the same initial pressure and temperature, and so that has a tendency to increase your mixture density. And then finally, your mixture composition also has an effect where as you change your fuel air equivalence ratio, right, your fuel and air have different densities. Right, so a leaner mixture will have a different density than a stoichiometric mixture. Right? You can kind of think through exactly what that trend behavior would be if a fuel air mixture has a higher density or a lower density at stoichiometric conditions versus at lean conditions. And likewise, your EGR level might have a small effect on unburned mixture density as well, assuming all other things are equal. Okay, so then what are the factors that affect the second term in our entrainment rate equation? And that would be the flame front area. So what are the things that affect the flame front area? Well, this is basically, if you can imagine here for just a moment, I go to my other notes here, and the flame front area is going to mostly be influenced by where the spark plug is, right? So if I have my spark plug over here as a side-mounted spark plug, then you can see that it takes quite a while for that flame to basically develop into a large area, right? And ends up taking on sort of a quarter circle type size to it, or type shape. Whereas if I have a centrally mounted spark plug, right, and so now perhaps my spark plug is in the center of the cylinder, well, now my flame takes on more of a hemispherical flame surface area, right? And so in this case here, my flame front area for the center mounted plug is going to be greater than the flame front area for my side mounted plug, okay? And then of course I can really increase my flame front area by adding two spark plugs, right? So if I have a spark plug on one side and a spark plug on another side, well, now I have flame front on this side and I have flame front on that side. And so I substantially increase my flame front area based on having a side-mounted spark plug, okay? And so you can kind of see what the what that effect is on how quickly we're able to burn a fuel air mixture, where we have, for example, a side-mounted spark plug. That would be the peripheral ignition. We can have a central ignition, which would be the center-mounted spark plug, or we could have dual ignition, where we have two different spark plugs, right? And if you take a look at this plot, this is basically showing you the burned fraction. This happens to be volume burned fraction, but you can think of it also as being mass burned fraction, or mass fraction burned. and this is plotted as the flame distance traveled divided by the bore, right? And so when the value is equal to 1, that basically means that the flame has reached the edge of the cylinder bore, okay? And so if you have a side-mounted plug, you can see that it takes quite a long time in order for that flame to eventually reach the side bore. Whereas if you have a central mounted plug, you're essentially able to reach a much faster burn fraction than if you had a side mounted plug. And then that accelerates even more, of course, if you have a dual mounted plug where you're able to reach 50% mass fraction burn sooner than even in the central mounted plug. And so, again, all of these are affecting your flame front area, right? These are all increasing your flame front area, where the flame front area of the peripheral ignition is less than the flame front area of the central ignition, which is less than the flame front area of the dual ignition situation. Okay, so what are some things that affect the next term in our entrainment rate equation? That would be the turbulent intensity, okay? So things that affect the turbulent intensity, these are all essentially ways that we as engine designers can purposefully design more turbulence into the mixture. So we can do that, for example, by changing the way that we design the combustion chamber. So looking at different types of shapes of the combustion chamber, whether that be a pent roof shape or wedge shape or hemispherical shape or any number of the other types of cylinder head designs that we might be able to come up with. All of these are more or less ways of trying to introduce more favorable fluid features into the mixture that is essentially increase that entrainment rate, increase the turbulence in the mixture, and allow the combustion process to occur at a fast enough rate. Another thing that we'll often do is we'll purposefully induce what we call swirl or tumble into the mixture. Okay, so what are swirl and tumble? Let me just advance a couple of slides, and I have a couple of pictures here that show you what swirl and tumble is. So swirl is motion around the center axis of the cylinder, right? So you see how the motion is basically, if this is our center axis here, the motion is around that center axis. Okay, in other words, if we were looking top down at the top of the cylinder, and this is my center axis of the cylinder, right, then swirl would be motion in this direction, okay? Or, it could be in the opposite direction as well. It doesn't have to be counterclockwise or clockwise motion, but it's basically swirl around the center point of the axis. So we can purposefully introduce that swirling motion in the fluid as early as during the intake stroke, right? And so essentially based on the way that the fluid comes into the mixture, if, for example, we have a certain design on the stem of the valve, we can cause that fluid, which is, to a certain extent going to be have a no-slip condition around this stem, that's going to influence the motion of the fuel-air mixture as it comes into the cylinder and basically create that vertical motion and maintain that vertical motion as the piston undergoes compression and eventually combustion. We can also have squish, which is motion toward the center axis. So if this is swirl, where we have motion around the center axis, then squish is going to be motion toward the center axis, right? So this is basically your squish pattern, okay? And very often the way that we design squish in is by having a bowl designed into the chamber. And so this bowl that you see here, as the piston moves toward top dead center, because you have this bowl pattern in the piston that causes the outer edges of the piston to force flow into the bowl region here. And as it's doing so, because of the lip and the various constructions that we have in this piston, it basically causes this squish motion and this additional turbulence within the mixture. Okay. And then we can also have tumble motion. And so tumble motion is now motion around the axis that comes in and out of the plane. So it's basically motion that is radial to the cylinder, right? And so at this point here now, This would be the axis around which, in this case, we have tumbling motion, right? So you can see how this tumbling motion occurs within the cylinder, and of course that can be oriented any radial direction within the cylinder, but you get the basic idea that you end up getting this tumbling motion within the cylinder itself. So with these three different fluid motions, they're all essentially meant to increase the turbulent intensity of that mixture. Okay, and the higher the turbulent intensity, the faster the entrainment rate. Now you remember that I said that the turbulent intensity is usually much, much larger than the laminar flame speed. We actually have some data to show you how that turbulent intensity is higher than the uh, laminar flame speed, right? So if you take a look at this plot here, these two plots, right, you'll notice that this is essentially that U prime. So this turbulent intensity that you see on both of these is U prime. And now this is as a function of engine crank angle. So this would be over a four-stroke engine where it's going from minus 360 to plus 360. And what you see, of course, is that the turbulent intensity rises to very high levels. Notice that this is 16 meters per second, right? Remember before, when we were looking at laminar flame speed, those values were centimeters per second, right? And so we're now looking at meters per second, okay? And so we're at a much higher level where, this would be essentially on the order of 1,500 centimeters per second, right? 1,600 centimeters per second. So we're at a much higher velocity, if you will, when we're talking about turbulence. Now also note, though, that as we get down closer to where combustion takes place, that turbulent intensity drops off quite a bit, but it's still much higher, right? So we're still, the laminar flame speed is somewhere down here, right? Where we're in centimeters per second regime, and this is 1 meter per second, which would be 100 centimeters per second. And so that turbulent intensity is still at the point where we're actually releasing the spark and starting the combustion process, still at the level of, say, 200 to 400 centimeters per second, much, much higher than the laminar flame speed that we had identified earlier. And of course, you see the same thing up here where we're between that 2 and 3 meters per second, or that 200 to 300 centimeters per second. Okay. And so what's nice about this plot too is it kind of gives you some idea as to how your turbulent intensity changes as you look at some of these different ways of purposefully introducing turbulence into your mixture. In this particular figure, we're doing it by changing the lift pattern of the intake valve, right? So if we have a normal lift pattern, those would be your squares that you see here. And then if we instead only open the valve to a quarter of the normal lift, well, that purposefully introduces more turbulence into the mixture, assuming that we're not choking our airflow. That's a way for us to purposefully introduce turbulence into the mixture and thereby increase the turbulence by almost 100 centimeters per second during the time of combustion. We can also increase the turbulent intensity based on how we change the spark plug and whether we have a purposeful high swirl valve or a low or zero swirl valve, right? So if we take a look at how the spark plug location affects turbulence for the two high swirl cases, those are these curves that you see up here. Okay, and you'll notice that in fact the spark plug has very little influence on the swirling pattern, or excuse me, the turbulent intensity when we're at the high swirl cases. But if we go to a low or a zero swirl case, even with a central mounted spark plug, our turbulent intensity drops quite substantially, right, by going from high swirl to low swirl. And so, again, you can see that based on the various designs that we can purposely put into the engine, we can change what that turbulent intensity is and thereby very strongly influence this entrainment rate, okay? Okay, and of course, we've already talked about laminar flame speed, right? So everything that we said before about laminar flame speed also applies when we do our analysis of the entrainment rate as a function of all of these various items. Okay, now at this point, we know what affects the entrainment rate. We know what affects the burn-up time. There's one additional item that I need to mention, and that is just to highlight the fact that our burn-up rate, the dmB by dt, which is of course the entrained mass minus the burned mass, divided by this burn-up time, this tau b. And remember that tau b is lambda divided by the laminar flame speed. So the only thing that we need to pay attention to in this context is what happens to lambda, okay? Generally speaking, lambda is affected by two things. It's affected by the unburned gas density, and it's affected by the turbulent intensity, okay? So lambda will tend to decrease as the unburned gas density increases, right? You can kind of imagine that, right? Where if I have a cylinder of low density, right, compared to a cylinder of high density, okay, you can see right away that that eddy diameter, that lambda, right, is much smaller when I have a high density compared to a low density, right? So this would be the low density case, and this would be the high density case. So by increasing the density of the mixture, I can decrease lambda. Likewise, lambda has a tendency to decrease as the turbulent intensity increases, right? And again, you can imagine that the whole point of U prime is to increase turbulence, right? The whole idea of U prime is to increase turbulence, which is to say, have a large number of eddies and so the more eddies you have, the smaller the diameter of each individual eddy. Okay. Okay, so you're gonna wanna remember those things as you start to prepare for exam number 2, for example. Okay, and again, the review session that you all will want to watch before exam number 2 will actually take you through an example of how you can use all of this information to actually assess what happens as you change all of these various parameters of an engine. Okay, so now what we want to do is we basically want to put this all together in a mass fraction burn curve. Okay, and so as we do this, we want to remember that there's basically two features of the mass fraction burn curve. There's the delta theta d, which is the flame initiation period, and remember that this is a function of basically just the laminar flame speed. Laminar flame speed is a function of a lot of things, but this flame initiation period is just a function of the laminar flame speed. The second item is delta theta b, which is our, I'm sorry, there's one other thing I wanted to mention about. Let me just back up here a minute. Remember that this delta theta b is the difference between your 10% mass fraction burn and your spark timing. And then the second period that we pay attention to is the rapid burning period. And this is now where we get our entrainment rate, dME by dt, which is equal to the unburned gas density times the flame front area times our turbulent intensity plus the laminar flame speed. And then that controls our burn-up rate, dMB by dt, because the burn-up rate, firstly, depends on the amount of mass that's entrained, minus the burn mass divided by the burn-up time. And the burn-up time, of course, is this lambda divided by the laminar flame speed. And of course, the rapid burning period, this delta theta B, is the time between our 90% mass fraction burned and our 10% mass fraction burned. So that's when the bulk of the burning occurs. So let's take all of this information and let's translate it to our mass fraction burn curve. So let's plot on the y-axis our mass fraction burned. So this would be MFB. And I'm going to mark on here 3 major elements, which we've already done in class. But this would be our 10% mass fraction burned. This would be our 50% mass fraction burned. And say this would be our 90% mass fraction burned. I'm also going to mark on here where top dead center is, just to kind of create a reference for us. Oops, that's not supposed to be 10 degrees. There we go. This is supposed to be 0 degrees, top dead center. Then I'm also going to mark on here where 5 degrees after top dead center occurs. And that's an important parameter, as you'll learn here in just a little bit. And the reason why is that in order for us to generally achieve maximum brake torque, okay, so generally speaking, as a rule of thumb, theta MBT, that is the spark timing that gives us maximum brake torque, is such that 50% mass fraction burn occurs around 5 degrees after top dead center. That's the quote-unquote sweet spot that gives location of peak pressure about 15 to 20 degrees after top dead center, which, of course, as I mentioned in class today, is where maximum brake torque, that's usually the location of peak pressure that gives us a maximum brake torque, gives us maximum brake torque, right? In other words, if the location of peak pressure is somewhere between 15 to 20 degrees after top dead center, that's usually around where maximum brake torque occurs, okay? So when we draw then a mass fraction burn diagram that is to result in maximum brake torque, that maximum or that 50% mass fraction burn point needs to occur somewhere around 5 degrees after top dead center, okay? So then we can, from there, map out the rest of our burn rate, which will look something like the following. Okay, and so this ends up being our mass fraction burn curve. And you can see now that if we define, for example, suppose this is our spark timing, theta S, right, which because our 50% mass fraction burned occurs 5 degrees after top dead center, also happens to be theta MBT, okay? And so we can then go ahead and define on here our flame initiation period, our delta theta D, and we can define on here our rapid burning period, our delta theta B. Okay? So let's suppose, for example, that we, say this is our base engine, and let's suppose that we increase our initial pressure by boosting with intercooling. So in other words, what that means is that our unburned pressure increases, but our unburned temperature will stay the same. Okay? What will happen to our mass fraction burn curve? Well, let's go ahead and take an analysis of that. So in order to do that, so we're going to analyze what happens as unburned pressure increases and all other factors remain unchanged. So for example, unburned temperature is the same, compression ratio is the same, fuel air equivalence ratio is the same, right? All of these things are the same. Let's take a look at what happens. Well, let's first of all look at our flame initiation period, delta theta D, right? Remember that the flame initiation period is a function of the laminar flame speed, S sub L. And the laminar flame speed is a function of fuel type, equivalence ratio, unburned gas temperature, unburned gas pressure, and EGR level. Okay? Well, this is the same as we increase the unburned gas pressure. This is the same. This is the same. This is higher, and this is the same. Okay? And then what happens to laminar flame speed as the unburned gas pressure increases? Well, let's take a look at our notes. So we go back to our notes where we have laminar flame speed. And what we see here is that suppose we're at some fixed temperature, maybe 500 Kelvin, and we've increased our pressure. So what happens to our laminar flame speed is that it decreases. So the laminar flame speed at a pressure of 100 or 10 atmospheres is less than the laminar flame speed at a pressure of 1 atmosphere. So our laminar flame speed essentially decreases as the unburned gas pressure increases. Well, since that's the only factor that affects laminar flame speed, and laminar flame speed is the only factor that affects the flame initiation period, if laminar flame speed is decreasing, then the delta theta D, the flame initiation period, will increase. In other words, it takes longer to reach 10% mass fraction burned. Okay, so I know that my delta theta D then is going to be longer as a result of me increasing the unburned gas pressure, just basically boosting my engine, increasing the pressure of the mixture. Okay, but let's see what happens to the entrainment rate. Okay, so, or the rapid burning period. So now remember that the rapid burning period, delta theta B, okay, depends on the mass entrainment rate and the burnup rate, dmB by dt. Okay, so let's take a look at what influences the entrainment rate, dme by dt, and that equals to the unburned gas pressure times the flame front area times the turbulent intensity plus the laminar flame speed. Okay, so if I increase pressure, if the pressure increases, certainly the density will increase. Right? We've held temperature constant, and so consequently, my unburned gas density will certainly increase as I increase my pressure. Okay, there's really no effect on the flame front area, AF, right? There may be an effect on U prime, but it's not easily known. And so we're going to say that there's no effect. And we've already established the fact that the laminar flame speed is lower as the unburned gas pressure increases. Okay? So in the net, the question becomes, is the unburned gas pressure going to raise the density more than the increased pressure lowers the laminar flame speed, right? What has the dominant effect? Right? In other words, does unburned gas density increase more than the decrease in laminar flame speed as unburned gas density increases, right? Or do they cancel? And truth be told, the answer for me is I don't know. I'd have to really dig into actually putting some numbers to this to make a quantitative assessment whether or not the entrainment rate is increasing as I increase the unburned gas pressure. So when this happens, I'll basically just say, well, I don't think that there's a net effect, right? So I'll say that there's no net effect, that the entrainment rate, dme by dt, of the high unburned gas pressure situation is about the same as the entrainment rate of the low unburned gas pressure condition, okay? So at this point, boosting the engine has really not done anything helpful, at least in terms of accelerating my burn rate, right? I have a longer flame initiation period, which that by itself isn't a big deal. So it takes a little longer for the flame to initiate. That's not a showstopper. It is, but there's certainly, at least on the entrainment rate, there doesn't seem to be any effect, right? Or if there is a net effect, it's going to be small because there's mitigating factors there, okay? But let's not forget about the burnup rate. So we have dmb by dt, and this is, of course, equal to the entrained mass minus the burned mass divided by the burnup time, tau b. Well, we've already established the fact that ME, the entrained mass, is more or less increasing in this equation at the same rate for the high pressure case that it is for the low pressure case. So that's largely unaffected by the increase in pressure. And the burn mass, of course, just depends on what that burn rate is. And so we can take a look at tau b, where tau b is lambda divided by the laminar flame speed. And again, I have lambda, which is going to decrease as the unburned gas pressure increases. But remember that the laminar flame speed also decreases as the gas pressure.
So once again, it looks as if there's no effect of unburned gas pressure on tau b, which is to say that the burnup rate for my high pressure case is about the same as the burnup rate of my low pressure case. And so if I were to then plot on my mass fraction burn curve this same situation where I now have basically the same burn-up rate, the same rapid burning period, the same 10 to 90% burning period with my high pressure case as my low pressure case, but I have a longer flame initiation period. In order for me to have the MBT timing, if this were, for example, theta for the low pressure case, and now I'm going to plot the same profile for the high pressure case, I'd essentially have to have my spark timing for the high pressure case be more advanced because my flame initiation period takes more time because of the longer higher pressure effect on the unburned gas pressure, but then eventually it would meet out because I have this timing set for MBT timing when my mass fraction burn curve passes through the 50% burn point. And so when I boost my engine, I have to advance my spark timing so that I have the same MBT timing so that I can achieve maximum brake torque when I boost my engine as when I'm not boosting my engine. Okay, so I like to choose the unburned gas pressure as an example because you get an opportunity to say things like, I don't know what's gonna happen, right? They kind of cancel each other, so I can't make an accurate statement here. And that's perfectly okay, right? You'll have an opportunity to do that on your exam number 2. And you'll want to review the review session to see how I do that analysis on the sample exam, for example. Okay, so the rest of the slides basically take you through different examples of what happens as we change various things, right? So as we change equivalence ratio, for example, you can see what a lean burn rate looks like compared to the stoichiometric burn rate, which we actually don't have on here. You'll notice that we go from 0.9 to 1.0, and so this is the 0.9 burn rate right here, and you'll notice that the faster burn rate is actually the 1.1